So I can kind of like
Yeah, yeah, exactly. That's what
I'm working on it.
The dictator.
I've been working about it.
Hell yeah.
I don't think I've actually watched the dictator.
Can you unlock the
Same.
player?
Yeah.
Thank you.
How do I do that?
Yeah, I was about to say that. My friend has watched it and he said it's very funny.
There you go.
We're watching it in about 6 hours from now if you want to join.
And now I gotta slip in Christmas songs mid like
Yes.
Is there a way to transfer, like,
Epic.
Can I do that?
Are you ready?
Okay. I used to be on VRChat a lot more in the early days, but I just
Make sure you hit record this time.
Lindixment.
right. Yeah, we added like 17 new VRChat Plus features. Yeah, I know you guys had one. It's this one feature was that on the back burner for 2029.
All right, everybody. May I get your attention? May I get your attention?
There's someone else who made the
Howdy, howdy. May I get your attention, everybody?
They had more. Like they got an entire.
All right. So,
and they packaged two of them.
we are starting the lecture in just a moment. So we are now streaming. Be aware, we're now live. We have our stream on the internal Discord. We should also be having our YouTube stream going. Just for a bit of housekeeping, we're going to be doing the lecture through video this time, and then we'll be having a Q&A session with Tholin immediately after. If you want to have any conversations, please keep it in the extreme corners of the room. There's also some area behind here, and it should hopefully keep the voices away from anybody who wants to watch the lecture. All right, so Tholin, take it away.
How do I start this? I think then. Okay, there we go. Okay. Hello. Welcome to my quaint little presentation. Today we'll be talking about. I will be talking about how precisely to not make an integrated circuit, because there's certainly a lot of mistakes that I've made over the years. For those who don't know me, I've been making custom integrated circuits for the past, I would say, like 3-4 years of my life, on and off. And it's certainly an exciting thing to do, especially when the thing you've worked on comes back from the fab after 6 months and doesn't work. And so today I want to talk about every single time that happened to me, so that hopefully people can take something away from that and learn to do better than I did. So let's get started. The idea of here's some of the things I've made. There's some layouts and one of the completed chips on like a little breakout board. The idea of making my own integrated circuits has stuck with me for a really, really long time. Pretty much ever since the day that I touched my first computer, I've been trying to figure out how they work and what exactly they do. And so the desire to learn more and more about that is kind of going down to lower and lower levels. My first like major programming language was Java, but I distinctly remember messing with assembly from like day one, basically. But there's always this insurmountable barrier, right? How does one make their own chips? Because this whole journey started like back in like 2014, 2015, when making your own custom PCBs just became a thing. So I did the next best thing I could, and I made this absolute monstrosity that is made out of individual, like, discrete logic integrated circuits. It is a processor. It works. I rendered a Mandelbrot set with this, and so those are my origins. And so clearly I had a lot of knowledge that I could already take with me when the opportunity finally presented itself to actually make a custom integrated circuits, when a couple of years later Tiny Tapeout splashed onto the scene. So for those who don't know, Tiny Tapeout is a service where you can get a custom integrated circuit layout manufactured for relatively cheap. It's like $100 to $200, because they just share the whole entire die area like 200 ways, and also share the cost like 200 ways. This doesn't mean you get relatively little area, but if you're just messing around, just learning, this is probably a good start. And there we go. And I believe that I, to this day, hold the record for the most designs taped out on a single tiny tape out run. I did like, I did 7 of them, which I was only able to do thanks to some support from the people at Tiny Tape Out. I also contributed back to some of their documentation. But this is not very important. What all I did, you can read the list if you want to. But I really want to highlight one particular design that was on there. I made this 4-bit CPU, and I made this at a time before I understood what a hardware description language is. So I would instead bust out Logisim Evolution, which has a method, has a functionality for exporting to FPGA netlists, and I kind of abused that to turn this into an input to the place and route tools to turn it into an integrated circuit. So this is a very, very old school way of doing it. So this is the top level schematic for this CPU, and I also have some notes that I took, because back then, anything that I started working on when it comes to logic design was started with pen and paper, and I think I still do that occasionally. It's generally a good idea to keep a lot of notes when you're doing these kinds of things. But another thing that I taped out that is related to this is oh no, hold on. Oh yeah, right. This is source code from the verification test cases I made for that 4-bit CPU, because even back then I realized that I should probably have some tests. Because at the time I was working a job where I just got off of a job, a software development job, that was heavily test-driven. We did heavily test-driven development, so I was like, yeah, why not? And Tiny Tapeout provided a Python environment that you could specify stimuli, inputs to your design, and it would run a simulation, return output. I got pretty excessive with this. I think this tests every single possible input, every single permutation into the hardware multiply and divide unit. And the whole thing, I ended up setting up this GitHub Actions workflow to run everything automatically, to run all the simulations. And then now we get to this. This is a peripheral that I taped out that is supposed to go along with that CPU. It's a sound chip. This is supposed to emulate these, retro sound chips, like programmable sound generators. Yeah, that's what they're called. Where you basically just have a bunch of integer dividers to generate various waveforms. This has 2 square wave channel, 1 triangle channel, 1 noise channel. But there's a problem, right? Because Tiny Tapeout supports only 8 inputs and 8 outputs on your design, or at least at the time, and a very low clock speed, because the way they would make it work is by essentially having a gigantic scan chain like JTAG inside the chip that would scan over all of the designs sequentially, and it was several hundred of them. It took so long that they promised us that the maximum clock speed could reach an absolute blistering 10 kilohertz on our chips, and ultimately that meant that I was having to figure out on my own how to get a faster clock, because 10 kilohertz, it's not even up to the top of the range of human hearing. It's halfway. And they did say that if we get one of the good chips, it'll be that fast. So I was expecting even less. And so I needed a faster clock to divide down to make good sounds, because if you think about how you divide down a signal of 10 kilohertz using just integer divisors to get smaller frequencies, the step size is huge for small divisors, and so you don't get a lot of precision between steps, between output frequencies, unless you have a fast input clock. And I decided that the way I would do this is by implementing a ring oscillator, which is this. So this is your standard Minecraft redstone clock, where you just have an uneven amount of redstone torches feeding into each other, and it never settles, right? Because these invert the signals, so it always goes in a circle. You can build this in real life, and it's called a ring oscillator. So this actually works, and you just need an uneven amount of inverters, and this will just generate output clock. And the more inverters you have, the slower it is, because you have to add up the propagation delay of all the inverters. And so I did that. I tried to do that, and when I first ran like the GitHub Actions pipeline to build the thing, it didn't give me an error. Like it didn't crash. But I realized that the simulation would actually hang up, like the verification simulation would actually hang, because right at the start it would try and find it would try and converge onto a stable state for the circuit, but because there's a ring oscillator in there, it just keeps going forever. And so within the actual test case, I decided to just emulate the ring oscillator in software by, instead of simulating the ring oscillator, just providing a faster clock input. So I wasn't actually simulating the ring oscillator in my simulation. And so this is the thing that I actually built. So this is made using AND gates and inverters, so I could toggle it on and off, which is important because these things consume a lot of power, and I didn't want to like increase the power draw of the whole chip because of my silly little ring oscillator, so I made it so it can be disabled. And to do that, I wrote some Verilog code that looks like this. And that's fine. That's technically code that describes how a ring oscillator works. That technically works. And so the big thing I want you to take away from this is to not do this. Do not do this. Do not do this. Because when you pass something like that into like a synthesis tool, which takes your code and turns it into logic, it will see this and it'll think this is garbage and it'll throw it out. So very likely what happened with my chip is that the ring oscillator didn't even get generated. There's no ring oscillator in there because it got optimized out, or rather, it didn't know how to deal with that. And this is the proper way to do it. So there is a way to forcefully instantiate logic cells, and if you do that, you can force it to put down a ring oscillator onto your chip. But you really have to know what you're doing if you do that. And also, even if my ring oscillator's on that chip, it's still blocked. So this is the specs for the inverter on the disintegrated circuit. So each inverter on this chip has these statistics for its delay. The second to last column shows the delay, and you can see it's measured basically in dozens of picoseconds, which means just 5 of those equal a clock speed that's probably in the like hundreds of megahertz range, which is way too fast for this chip. That would have completely overwhelmed it. That's way too much. So even if the ring oscillator is on there, it's generating a clock that's too fast for what the cells on this chip can handle. So either way, I'm screwed. So also, if you're gonna do something that requires messing around with stuff on the actual like hardware level of the chip, like you need to know the specifics of what you're working with, and that's also always worth checking if you're doing things that rely so heavily on the actual logic cells. Now, the next thing that I tried submitting to this tiny tapeout was a program that just sends some messages onto a character LCD, like you see here. Now, this is a still frame from a video of it in action, and what you don't see is like a second later when the entire screen glitches out and is just filled with garbage characters. So it turns out that in order to generate a delay between messages, so these stay on screen for a few seconds, I decided that I was just gonna spam the LCD with what I thought was a no-op command, because the LCD command bus can't ever be inactive with the way I programmed it. So I was like, okay, I'm going to spam a no-op to the LCD during the delay periods. And it turns out it's not a no-op. Whatever it is that I'm actually sending, it's messing up the LCD, and it causes the entire thing to glitch out in between messages instead of just pausing. And which just surprised me because I was testing this. Like I was using a simulation of one of these displays, like a live simulation on my computer, to test that my chip was doing what I wanted to do. And there we go. And well, it turns out that simulation model had edge cases. It didn't actually check all of the LCD commands. It just checked the ones that like most people would use. And so it treated what I was sending as a no-op, even though that's not what real LCDs do. So if you can use like third-party simulation models for verifying what your chips do, check them. I always check them over. Make sure that whatever it is that you're actually if the hardware is properly simulated, or at least present in the simulation. And yeah, just do that. I don't just download a model and think it's perfect. And when in doubt, just check the datasheet. Actually, just always check the datasheet. This is not the only time I will make this mistake. We will actually get back to that one. Now, the next opportunity I got to tape something out was doing a open shuttle. So the tiny tapeout chips actually ended up taking over a year to get delivered back to us because there was a lot of delays. And so my tiny tapeout chip was still the fab when this happened. So there used to be something called the Open MPW, or Open Shuttle program, where you could get a fully customized seat taped out for free. This would run 4 times a year, and there would be 40 slots per one of these shuttles. And all you had to do was submit your layout that you wanted to get made. And of course, there would be more than 40 people doing that, and so it would be like random chance. They would essentially roll a lottery for who got the 40 slots. And this was, however, this one was done on a different process node than usual. This was the first shuttle to be taking place on the recently open-sourced 180 nanometer Global Foundries node, specifically like a 5-volt variant designed for microcontrollers. And the deadline was in 2 weeks, 14 days. Actually, I think it was like 15 or 16. Not really too much of a difference, though. The deadline was, well, quite soon. So I realized that I couldn't make something from scratch, even though I wanted to. There was just not enough time. And I probably had better chances implementing an existing design. And I wanted to still make a processor, a CPU. And there was this old 8-bit processor from the 70s I'd recently become obsessed with. This completely abandoned CPU architecture from Signetics, the 2650. I kind of become obsessed with this. I think it's neat. I think there's some neat aspects about it and the way it's implemented. But this CPU architecture was a commercial flop, and Signetics discontinued it like before I was even born. And so I decided I'm just going to revive that. I'm just going to re-implement this, but on this process node. And this was going to be my first major Verilog project. I had just begun learning my first HDL, basically. And so this is when I get back, like 6 months later. So I actually received these before the tiny tapeout chips. So I go through the whole process of designing this 6 months to the fab, and I get them, and the tiny tapeout chips are still like sitting in delays. And it's the layout that's on there. So that at the top middle, that is like the square there with all the pink. That is the CPU that I made. And well, I would say it didn't go so well. The bug list for this CPU is 9 items long. It can't even add or subtract numbers properly. Like it can't add. And an entire like addressing mode, entire memory addressing mode in one of the instructions is just broken. It doesn't work 90% of the time, and the whole thing is bound to like a maximum clock speed of 25 megahertz if you're lucky, because of some architectural problems. The thing is, it's not exactly. I wouldn't say it's running. It's not running. I would actually say it's like barely standing on its 2 legs. It's just kind of shambling forward. That's what this thing is. It's not running. And well, to kind of explain this is important context, not just for this, but something in a bit. At the time when you taped out with eFabless, which is the company that was doing these things, you would not just tape out your own design. And what you would do is you would submit a layout, and they would embed that layout into a pre-made pad ring, which has the I/O pads, and you would attach something called the Caravel Management Controller at the bottom, which is what you see here. You can see the user project there at the top, and then like the quarter of the die is this management controller. They put an entire RISC-V microcontroller on there, which has logic analyzer probes and a wishbone bus, and like everything you need to verify your design on die without attaching anything. The thing can even take over the GPIO pins and generate artificial stimuli, which is great. But it presents an issue because you don't know what specific pinout for the chip that the user wants. Because this is supposed to be a general purpose like pad frame. So each of the like I/O pads on this chip that communicate with the outside world can be reconfigured at runtime by the management controller to be inputs, outputs, bidirectional, analog, whatever. But there's also a power-up configuration. there is a little text file, basically a CSV that you send to eFabless that has the listing of what each pin is by default, and that's the state it will power up in, and then you can reconfigure it with the management controller if you want to. And well, I messed that up. I got the config completely wrong. I accidentally confused the GPI mode management prefix with the GPI mode user prefix, and as a result, all of my GPIO pins were being rerouted to the management controller instead of my CPU. And as a result, the AS2650 has no pins. When a chip powers up, the AS2650 is completely isolated from the outside world because all of its GPIO pins are cut off. Which, you know, great, it's in there, it technically works, can access it. Well, this is fixable. The management controller can just run a little program to update the GPIO lines, and it's great. Right? Well, it turns out I accidentally used the exact same pin to generate a reset signal for both my CPU and the management controller. I wanted this pin does double duty, and I was later on advised it's not a good idea. You shouldn't tie your design's reset to the management controller reset line, because then you can only reset them at the same time and not like individually. And that means that immediately after applying the new IO config, the CPU is in its glitched state. Like the whole thing that I made enters a glitched state during like a second it takes the management controller to fix the IO pins, and so I need to reset it. But that also resets the management controller, which makes it rerun the code to update the IOs, which enters the glitched state, and it like makes it rerun the... Yeah, it's an infinite loop, it keeps going. This is sort of fixable. You can like detect whether or not this is first power up by checking if there's a magic value in RAM. But it's like a little inconsistent, but it works most of the time, so it's like... I could at least use my CPU, even though it's a pain in the ass at this point. So I can use my CPU now, right? But is it any good? Well, what exactly is not working right? There's a CPU flag called the interdigit carry, which is not being generated correctly. But this is some like binary coded decimal CPU flag. I don't care. I genuinely don't care. I don't need this. So just whatever. The indirect relative address, the branches are broken. So the indirect relative address branch instructions, they branch the program to another location, and they read the pointer to that from memory. So it's like a pointer dereference, like a function pointer dereference. And the relative version of that is that they're broken. They just don't branch. They just don't ever do anything. They're just gigantic no-ops. Even the unconditional variants of this branch instruction don't branch. The fix for this is in software. The indirect absolute address branch instructions do work. It just means that my programs can no longer be position independent in this aspect, because relative addressing is like relative to the program counter, while absolute is just an absolute memory address. And you need the former for position independent code. The whole indexed addressing mode only works on load and store type instructions. Indexed addressing is like this, where you like load a register from some memory location indexed by R3, and what it does, it adds the value of register R3 onto the pointer memlock and then loads from that. It's a pointer dereference, essentially an array access, like in most programming languages. So this instruction works. Doing it with a load instruction works, and doing it with a store instruction works. Doing something like this, where you use this addressing mode on something like an add, so you add from this dereference address, does not work. It breaks. It does some glitched operation. Sometimes crashes the processor. It's great. Which means that of the entire instruction set, there are 2 instructions for which this addressing mode works, and 6 for which it doesn't. So that's not a great rate. The next bug is that the return from subroutine instruction, which you use for returning from functions, basically takes 256 clock cycles to complete, which is way too long. It should take like 4 or 5 clock cycles, but it takes 256 clock cycles to complete. This is a bug in a finite state machine. Like most modern processors, I'm using a finite state machine to implement the actual processor loop. I'll explain that in a moment. And I'm using an 8-bit counter to index the current state. And this counter counts up by default, and only when the state machine requests to jump to a specific state does it do that. And it turns out that at the end of the return instruction, it forgets to reset this counter back to 0. And so it just cycles through all states and it wraps around naturally, and that takes 256 clock cycles. And that's not good. It takes around 256. A finite state machine looks like this. So this is a little implementation detail for this processor. So this is actually for a very basic MIPS core. This is not for mine. But you essentially start in the top left, where you have a bunch of steps for fetching the next instruction, and then it looks at what the instruction is, and depending on what type the instruction is, it branches to different other states, where it says like branch, or put stuff into the ALU and get the output, or do some memory address calculations and either read or write from memory. And so this is a pretty logical way of implementing processor logic. Except I messed mine up. It's actually the only time I did that. The push instruction it writes to the wrong location. It's supposed to be a stack push. It turns out that I messed up the stack pointer decrement. You're supposed to decrement the stack pointer and then write to memory, not the other way around. Whoops. Yeah, then the address ends up off by 1. So now so there's another addressing mode issue. Indexed indirect address store instructions do not work. This is when you dereference a pointer out of an array. So it goes to this memory location, reads a 16-bit value as a pointer, indexes it, and it's like a 2 levels of dereferencing basically. And it just does nothing. Like, it doesn't do anything. This is pretty bad. It's usually a pretty useful addressing mode. And it just makes index addressing even more broken. Like, indexing is just fucked. Now we get to the big one. The CPU doesn't know how to add or subtract. It's, when you add 2 numbers on this processor, it computes R plus V plus C, where R is one of the register values, V is the value for memory or register, and then C is the carry flag. Because you might want to add numbers that are bigger than 8-bit on this 8-bit CPU. So you have to split up, like to add 2 16-bit numbers, you have to do 2 additions. But you need to keep the carry from one stage to the next, like you would in decimal. And so this results in having to add to the carry, and it also generates a carry. Essentially, it outputs a 9-bit result. And so, for instance, if you were to add 255 onto a value R and the carry flag is set, so you're basically adding R plus 256, it wraps around, you get the value R, and you get 0 in the carry flag. Except, no, that's not correct. You're supposed to get 1 in the carry flag. If you think about this in the binary sense, 256 is basically ninth place. And if you add 256 to anything, it just sets 9th place to 1. It's like adding 100 to 10. All it does is just basically smash them together. And, well, so essentially mathematically this means that the CPU incorrectly asserts that R plus 256 is equal to R, which is incorrect. That's not how math works. And subtracts is also broken. The CPU will, because the adds and subtracts go through the same circuitry, and so it subtracts, if you subtract 0, it asserts that that's equal to minus 256. That's really bad. It's really bad. Because my code, because I can walk around everything in software, but my code becomes so bloated from having to detect and manually fix these edge cases. Like, instead of just being able to add 2 numbers normally, like this, I have to copy paste this whole thing each time I want to add 2 numbers. This just a bunch of conditional branches and tests that detect a specific case into the addition of plus 255 and the carry flag is set, and then applies a fix. So it's pretty bad. It's bad. That's the conclusion. It's bad. Well, how did this happen? Because everything went so well during Tiny Tapeout. I was doing all these simulations, I was doing all this testing, and the only time it failed me is when I stopped doing the testing. So I did verification on this processor. Ryan, I did that? Well, it turns out that actually my method of verification on this was, well, you'll see. Because on the Skywater Foundry's 130 nanometers node, which is what Tiny Tapeout was on, the Fabless provides a whole testing framework, a whole simulation framework for simulating your entire chip and making sure it all works. And it can simulate not just RTL, which is just running the Verilog. It can also do something called the gate level simulation, which simulates the actual logic gates one by one on the chip, which is very accurate and generally gives you a good idea of how the chip's timing works out as well. And we didn't have this on Global Foundries. It was broken. And that meant that I had to throw together my own thing. I tried to throw together my own RTL-only environment using something called CocoTP, which lets you write test cases in plain Python. And, well, it turns out that my testing strategy consisted of starting a simulation of the CPU and some simulated RAM, letting the CPU run a short program that I manually created, and then checking if the output of that program matches the expectations. And that's it. End. Simulation end. So that's it. That's it. There's nothing else going on. It's just like run a short program, and if it's okay, it's okay. So what's wrong with that? What's wrong with? Let's analyze that actually, because I once thought that was a good idea. So let's analyze why it's not. Well, first of all, you don't have individual test cases for each instruction. Whether or not an instruction even gets tested or not relies on whether or not it occurs in your little test program. And even though I tried to include every instruction, that doesn't mean I tested every single possible opcode. Because, you know, assembly language and machine language is not one-to-one. The simulation also does not check that the CPU does what it's supposed to at every clock tick, which is how, you know, things like finite state machine the bugs get hidden. Because for instance, I was simulating the return from subroutine instruction, but I just cared about it, you know, doing its thing properly and how long it takes. So I didn't discover that it takes 256 clocks. I was not checking the bus cycles, like on the pins, and on top of that, I was simulating using an ideal RAM model where memory is like infinitely fast and stuff like that, which is also how I didn't discover that there was some latency issues. And of course, if I'm manually assembling a test program, then I'm very likely to skip over edge cases. And in general, I had a low opcode coverage with my little program. It wasn't even a good test program. So, what should I have done to make this a better CPU? Well, I should have made it so that my finite state machine didn't even have undefined states to begin with, which you can enforce by making it halt if it hits an undefined state. Instead, the way I programmed it, it just like increments this counter each time, so if it hits an undefined state, it just keeps incrementing until it wraps around, which is in itself undefined behavior. FSM bugs can easily be caught if you implement guards into it. I should have factored memory addressing calculation out into clear states, like individual FSM states. Instead, the way I wrote my code is I would jam like memory addressing calculations into whatever states were available and free, instead of just making it like its own section in the code, which would have helped with organizing. In general, keeping your finite state machine as simple as possible, like you saw with that MIPS processor, is a good idea, and you should also document it. The reason I showed you the FSM from a MIPS core instead of this processor is because I didn't document anything. I didn't write a diagram or anything. I didn't even name the states. I didn't even name the states or the signals. Yeah, here's a screenshot of some really horrible code. Like, what even is this? This is actual source code from this project. I didn't, like, I guess this like detects something about the opcode and like fires something if it's like a specific instruction, but I could have like named those individual conditions. I could have like how you're supposed to name variables once you know your statements get long enough in a regular programming language, just to make it more readable and to make me understand what's going on. So ultimately, it also boils down to this: what would you rather have? An instruction that takes 1 clock longer to execute, or one that doesn't work at all? Because a lot of this like code garbage was in pursuit of performance. I was like, yeah, if I can merge these two FSM states in a really awkward state, I can speed these instructions up by 1 clock cycle, and then I end up just breaking things and making them confusing. So there was actually a trade-off between performance and readability of the code, at least in this case. Although, you know, I decided to just not have any good code style at all. That's very important. You just saw an example of that. It can drastically make it easier for you to work on your code, especially if you're in a tight deadline. And generally, this whole project was really an exercise in time management, because I had a deadline of just 2 weeks, and I had to allocate that time to different tasks, development, verification, primarily. And if I really should have sunk more time into verification instead of development. Again, I wanted this thing to be fast. I wanted it to have all of these bells and whistles, and so I put time into development and not into testing. And it's not what I should have done. So, if you're on a deadline, you should really make yourself like a schedule or something. Have some kind of idea of how you're breaking up the time that you have into manageable units. And yeah, that's budgeting your time. And also learn about the tools that you're using. There's a number of bugs that were caused by peculiarity of the way the Verilog standard is defined. If you look at this code here, well, this is just a very simple condition. This is like not really weird, except that the variable dbuzin does not exist. This is a non-existent variable, in fact, because I renamed it at some point and I forgot it in this one spot. So what exactly is supposed to happen according to the Verilog spec when you try and synthesize something as an undefined variable in it? Does it 1, generate an error and stop? Or 2, does it silently replace this with a constant 0 and continue? The answer is 2.
That's so cursed.
I checked the logs. I ran this. After I saw this, I couldn't believe it. I looked at the logs, and it turns out it doesn't even emit a warning message. It just does it silently without telling you.
Wow.
According to spec, you're supposed to have You're supposed to have this line at the beginning of your code to make it fail when it encounters something it doesn't know. You're supposed to have that at the beginning of your code, but didn't know that. There was like some, from my perspective, as someone just starting out, there was like some deep insider knowledge that the syntax exists. And of course, hold on. And of course, I didn't realize that there would be some physical limits to the way this works. The CPU and the way I programmed it is it expects memory to respond within 1 clock cycle, basically immediately. It throws an address out on the bus and it's like, hey, can you do this, memory? And it just waits 1 clock cycle. And the original Signetics 2650 had an OPAC pin which you could assert to, or deassert to make it wait for memory, to make it insert additional clock cycles of idle time. And I did not implement that. I thought that was useless. I thought I didn't need that. And, well, it turns out that even really fast SRAM memory is too slow to keep up with the demands of my little processor. This also has to do with the fact that the signals that, they have to go through these physical I/O pads, and those add a lot of latency, which I didn't understand at the time. And so ultimately my design, it's capped at 25 megahertz, even though the timing analysis passed for 50 megahertz. What are some minor things? I did not make enough use of Caravel. If eFabless is going to force this a little microcontroller at the bottom of my chip on me, if I have to have it on there, then I might use it. I did not hook up anything to the Wishbone bus. I did not hook up anything to the logic analyzer probes. Not that that would have helped me fix anything, but it would have made debugging a lot easier. And generally, I came very, very close to realizing most issues of this design because I was thinking, well, I have a bunch of software for the original Signetics 2650. Why don't I try simulating that or running that on my thing? And I didn't because I ran out of time by 1 day. And I really recommend doing this. If you're emulating a commercial design, just try running some real-world software and sort of your own test cases, see if it works. We have FPGAs for this as well. And however, I did actually end up making something cool of this. This is the badge I took with me to Eurofurence 2 years ago, or 3 years I think at this point. And at the very top left, it has one of those custom chips with the broken 2650, AS2650. And it has a little bit of RAM, it has this little CPLD for display controller, and with all of the software fixes I found for walking around all the bugs, this thing has a little demo on it where it runs a software 3D rasterizer and renders in Avali. Not this though. That's just an image. Yeah, so now we skip ahead a year to November 2023, and the OpenMPW program has been killed. It is kill. Where were you when OpenMPW was kill? So they basically said no more free shuttles. We're not doing this anymore. And a year later, they were like, actually, we can do it one more time. One last time. Oh, the microphones are glitching out. One last time. on the exact same process node with Global Foundries. And this was my last chance, because at the time it really seemed like there was no way to tape out your own silicon. It was like more complex than what you could fit on tiny tape out without shilling out over $10,000. And I was like, okay, this is the last chance. This is the only chance that we'll get. This is the last time I ever get to do this, and I have to move on with my life. Spoiler alert, that's not how it worked out, but the AS2652, or version 2, I was like, okay, I can fix this. Right? I've leveled up my skill in the intervening year. I can do this now. And I also did like 11 other things. And this time the deadline is 5 weeks. So that's a little bit better. It's like one month and a week. And I was going to unleash 100% of my power. You're about to witness what it looks like. I'm not joking. I burnt myself out so hard I couldn't work on any projects for like 6 months. So the plan is that the version 2 of the CPU that I made is not just going to be fixed, but upgraded. Same CPU core, but I add some of my own custom instructions, like a whole page of additional instructions. I was going to add a more sane external bus interface, and I was going to give it interrupts. The original had no interrupts, and it also made my life hell at some point. And I was going to build in peripherals, an I/O ports, timers, counters, serial ports, a C64 SID, because I could. And I was going to put RAM in there, because now, during this shuttle, we could leverage the SRAM, like the fab-provided SRAM macro. So it's like, okay, I'm going to spam SRAM in the remaining die area, and it turned out to be 4 kilobytes. And a little bootstrap ROM, so the CPU can boot off of a SPI flash, and then run off of only the internal RAM. You don't need to hook up anything externally. And to make this whole thing configurable, I was going to use Wishbone bus on the management controller. So here's what it looks like. You can, at the bottom, the copies of the many copies of one similar looking thing. That's the RAM. The large block to the middle left is the CPU, and then you have the peripheral blocks next to it. I also learned how to put like art on my chips. So that's what that looks like. And also this time I was going to do verification properly. I made test cases for every single instruction for pretty much every edge case that I could think of. I tried to get as close as possible to 100% opcode coverage. You can see the one on the top left that's called add sub. I made a test case that iterates over every single possible permutation of the addition and subtraction, which is about 512,000 test cases each. It takes like 8 hours to run, but it gave me peace of mind. So after I did this, because making the version 2 of this thing only took me 2 weeks, which is ironic in hindsight, but I still had time left. I had the majority of the time still left, and was like, okay, there's nothing in the rules that says I can't submit to the same open shuttle twice. So I was gonna shove multiple, because I had many ideas for custom chips. So I was like, why don't I do all of them and shove all of those individual ideas onto a single die using a gigantic multiplexer to share the I/O pins between them, similar to tiny tape out, just a faster setup using a multiplexer. And I named it simply GFMPW1 multi or GF multi. That's the name of the chip as a whole. And what did I put on there? Well, I put an LED blinker on there. Of course, you have to. It's mandatory. I created a replica of the Commodore 64 SID, and I put 2 of them on there, and dual SID setup. I reached out to someone who also had some ideas, and they contributed some other programmable, like retro programmable sound generators. The failed sound chip that I tried to make during tiny tape out, I taped it out again. Hopefully it works this time. I don't need the ring oscillator this time. I have a fast clock. And I was going to make a bit serial 8-bit CPU, using that's based on like the MC14500 1-bit CPU architecture, because I realized I could make this like absolutely tiny little thing that is still Turing complete, which it is. And I tried to challenge myself. How fast can I design a custom CPU architecture, implement it, and verify it? And I did this in 8 hours, and I call it QCPU. So that's apparently how long it takes me to do all that. And I also resubmitted one of my tiny tape-out projects, just as like a memorando. But that's not all. I also put a thing in there that generates UART frames for this like messed up hello world message. If you know what this is reference to, you're cool. Also like another like bit serial processor. I tried to make a PDP-11 4D compatible CPU upon popular demand. And on the very last day, like literally it's hours before the deadline, I'm chilling in an instance of Resonite with one of my friends who actually went to university for integrated circuit design stuff. And I was like thinking out loud, like, it's like 8, 9 hours left. Like, is that enough time to make like a RISC-V core? And she was like, yeah, no way, that's not enough. And the problem of doing that to me, the problem of saying something like that to me is it becomes a challenge, and then I have to defend my honor. So it turns out it takes me 8 hours to do that. It's only an RV32 IM core though. Okay, so so that's what that looks like. So on the left is the layout, and on the right is just a map of where everything is. It's a lot. I basically just crammed the whole thing full. I think I have like the second to most die utilization of anything that was submitted. There's someone who made an FPGA, and that has like almost 100% die utilization. And that's what it looks like back from the fab, because this time I actually didn't just get chips, which you can see here, but I also got raw dies, which you can see me holding on the other finger. So I got both chips and raw dies, and so I can take like cool microscope photos. It's really cool because you can see the Avali logo. And, you know, because there was, you know, one of the projects has like a bunch of things on it, I needed to make all of these PCBs to bring them up. So the top left is for bringing up the bit serial processor, bottom right is for the PDP-11 compatible, and bottom left, that's the RISC-V core, that's me testing the RISC-V core. It has like a UV EEPROM in it, and the idea that I'm using a UV EEPROM together with a RISC-V core is like never not amusing to me. I love this thing. And yeah, I did some test cases for this as well, although I didn't do exhaustive tests. Like I didn't, like for instance, for the PDP-11 thing, I didn't test every single possible opcode. I didn't even try because I didn't have the time. But this time I decided to accept the risk that some things might break because they're unverified. So this time I knew what I was doing when I was intentionally making mediocre test cases. I just wanted to get as many ideas into the die as I can. I had to get the ideas out of my head. So I get the chips back and I test everything. The bit serial processor works perfectly. The RISC-V core has one minor bug with a timer interrupt because I didn't test an edge case and I didn't simulate an edge case and it's broken. But it's fixable. It's fixable in software with just a single instruction, so it's fine. The SID core, the C64 SID works perfectly. It makes all the beeps and boops and all the other noises it makes. The other two PSGs, I shipped some chips off to the person who contributed those layouts. I've not heard back yet, so we'll see. All of these also work perfectly. And you know, but you know, we're glossing over that. That's not what today is about. I could talk for hours about those designs and like how cool they are, but that's not what we're doing. We're talking about how I messed up. So let's enter QCPU, or which stands for Quick CPU, because that's the thing I speedran in 8 hours. And it has issues, unsurprisingly. So it's supposed to be an 8-bit Harvard architecture RISC microcontroller, which is like inspired by RISC-V, but 8-bit. Although the instructions are 16 bits wide. It has built-in GPIO ports, timers, PWM channels, and interrupts. And there is 64 bytes of RAM on that die that are actually shared between the different designs. For instance, the bit serial CPU uses that one as well, and so I could use that as well for this one. And for the ROM, I wanted to hook up an external ROM because we had like no like flash macros or anything like that. We have OTP cells, like one-time programmable memory cells on GF180, but that's it. I didn't want to mess with that. I wanted it to be programmable. And so I decided to use one of these. I love these things. I love this. Is like a WinBond flash IC, and these things are really neat. I use them in basically, you can see this in basically all of my projects somewhere. And by default, they are SPI. So they use the serial peripheral interface, which is, you know, a serial port. So 1 bit at a time. However, they have an optional QSPI mode, which is 4 bits at a time. And the speed difference is quite stark. If I were to use SPI mode, it would take 32 cycles to fetch one instruction, 32 clock cycles, for my QCPU. But if I used QSPI, it would only take 8 cycles. And then instruction execution takes 1 clock cycle. So the memory bandwidth is the bottleneck. So I need to optimize that. So of course I choose to use the QSPI mode, but it turns out that entering QSPI mode on these chips is not straightforward. You have to issue a command sequence consisting of a release from deep power down, a continuous read mode exit, a write enable, then you write one of the status registers to enable quad read, then you send a quad read command, but this one's just a dummy actually to enter continuous read mode, and then you can issue your actual quad reads that you want to do. So this quite complicated reset sequence, it has to do that on reset, on power up. So I found some simulation models. I was like, okay, the official Winbond Electronics Corporation Verilog model for this flash chip. There's like a copyright notice on there somewhere. I didn't screenshot it. It is the official model. So this is from the manufacturer. And if I use that, it looks fine. So even if I don't explain what all of these signals on this graph mean, you can see it's doing something, it's walking, it's fine. However, that's not what ended up happening. So first of all, QCPU runs at 5 volt. GF180 is a 5 volt process node. The QSPI flash is a 3.3 volt device. So I need a level shifter. And it needs to be a bidirectional level shifter for QSPI. And so I added an output pin to my chip to control this level shifter. I didn't simulate it. I didn't test it in simulation. And of course, it's broken. This is fixable with the use of, with a clever use of some 7.4 series logic ICs and some analog circuitry. It's actually fixable. But it's so just annoying because this was supposed to be a 2-chip solution, right? You have my little microcontroller, you have your program flash, that's it, you're good to go. And now I need like 2 other ICs just to fix this bug, and it's not great. Now, it still doesn't work. Right, I find this walkaround with 7.4 series logic. I verify that it's actually working using an oscilloscope, and it still does not work. It's not getting data back from the chip. Well, it turns out that the status registers in the chip that you can program are stored in flash. So even though it says registers in the name of the control and status registers, they're actually flash memory cells. And these cells hold like configuration bits for the chip. And, well, turns out that flash needs some time to be programmed, so whenever you update a status register on this thing, it takes 1 to 2 milliseconds to charge and discharge the flash cells. And if you try and send any more commands during this time interval, the flash chip locks up, it crashes, it basically hard crashes. And, you know, remember that official Winbond Verilog model? That's great. It even did some, like, timing analysis in there, it's awesome. It turns out it is not accurate to reality. If a 30-second look in like a single table datasheet, and I see that the flash needs this time to be programmed, and the model is like, yeah, I don't care, just do it instantly. And so there's this discrepancy that I could have easily found if I had just RTFM. That's my advice. Again, I told you this would come to bite me a second time. And you know, if you're gonna get something that's like a model from the internet, you should probably check the code yourself. Like, you should actually like open up the source file, and you should, for whatever like special commands that you're sending and checking, then it does exactly what you think it does or what it describes in the datasheet if you're unsure. The good thing is the management controller comes in clutch. As I said, there's this little microcontroller on the chip that can take over I/O pins, and I can program it to override the chip select line to the flash on a very specific clock cycle to inhibit the write status register command, which is the command that crashes the thing. And because the status registers are non-volatile, I can pop it into a program at my PC and pre-program it how I want it to, which is a little bit annoying, but it works. Here's what that looks like, by the way, because I need to like fire a signal on a specific clock pulse, this inline assembly. The thing has like an instruction cache as well, so there's like a bunch of no-ops to flush the cache. It's great. Well, now we get to the AS11. This one is a really interesting issue. This one's supposed to be PDP-1140 compatible, but while it is still at the fab, I discover some issues. Even though it looked promising in a simulation, all of the test cases pass, I could even run C programs compiled by the GCC. The GCC has a PDP-11 target. It still has that. You can use it. And I found these issues before I even got the chips. It turns out that the divide instruction, the hardware divide instruction, is not working correctly. The whole PC relative addressing mode is wrong as well, so we get that again. But it's not like broken, right? Because my test cases pass and everything looks fine in there. When I say wrong, I mean it's different from the PDP-1140 spec that I've been referencing. It turns out that these instructions, like, they're completely fine instructions. The walk is verified, they're useful, you can use them, it's all good. But, for instance, the only thing that's really broken is that the divide instruction does not produce a modulo output, even though it's supposed to. It's the only really breaking thing. For instance, the PC instruction, the PC relative instruction, which are supposed to index something relative to the program counter, they index from the start of the instruction, from the end of the instruction at the beginning, which is how the PDP-11 does it, which is like a slight difference of like 2 bytes, but it completely breaks all existing binary compatibility. So we're going to say it again. Read the manual, please, because this happened because I was reading the PDP-1140 spec and I was not reading correctly, and I didn't come back to check what I thought was correct about how well PC relative addressing works. But it's a completely fine processor. I built a custom assembler that assembles these instructions correctly into the correct bytecode for these quirks, and it works. And also one thing I can recommend is look at some example code. The PDP-11 is a very popular architecture. You can find tons of binaries online, of existing binaries, and you can just run some of that code and see if it does what it's supposed to. It's not difficult. However, next issue I have is I wire middle test board, and I'm using FRAM, which is ferromagnetic memory, and it's supposed to be like a callback to how the original PDP-11 used, what's it called? Like core memory. No, the original PDP-11 was core memory, like actual, like the little ferromagnetic cores of the wires woven through them. So it's like, I'm going to use FRAM. There's like a reference to that because it's also using a similar method. And because I had a pin count limitation, right? Even though the chips come in this little QFN package, the amount of usable, like actually usable pins is about the same as a DIP40. And it's a 16-bit CPU. And so I realized that the only way I could make that work is by multiplexing address and data onto the same 16 pins, which looks like this. So you can see the second signal from the top is the address latch, or the latch enable. And whenever this is active, it means that what's appearing on the chip outputs is an address and not data, and that the address should be latched. And you can see that the signal is actually half a clock pulse wide. It's not a full clock, because that might cause hold violations in the latches. And so how did I do that? Like, how do I make a signal be half a clock pulse wide when everything in the chip happens on rising clock edges? Well, I decided that I was going to do this by... Well, first of all, here's what I saw on the RAM. Just cut and right do that. I tried sampling one of the output pins on my FRAM with my scope, and you can see there's a second spike to the right. Like that on the left, that is the data that's supposed to be coming out of under that like specific bit line of the RAM. But what's that? That spike is like this like nanoseconds wide. That's like way faster than a clock. So what's happening there? Why am I getting like glitches out of the RAM? And well, this is what I decided to do to make this signal half a clock pulse wide. It was just gonna take the signal, like the actual signal, and then AND it with the clock, just like AND clock, because then it would only be active during the active phase of the clock, and it's great. It works. To better portray it logically, you have this. You essentially have an AND gate connected in between the clock and like some like register that holds the state. But the problem arises that if a positive going clock edge comes in, like the clock goes high, then it takes some time for the flip-flop to update its output from a 1 to a 0 and to become inactive. But the AND gate is much faster at propagating its thing than the D flip-flop. So for a brief moment, the output of the AND gate becomes high before the flip-flop finishes propagating its 0 and turns the AND gate back off. Unfortunately, my animation here seems to have broken to show that. And I have another oscilloscope trace for this, where you can see... We can actually see the glitch. You can see this trailing positive pulse and on the bottom line. If you can't spot it, it's right here. It's really tiny. It's like 2-3 nanoseconds wide, which my scope can barely pick up. But the modern FRAM chip can absolutely pick up. the FRAM chip sees the second pulse and it's like, oh, I need to latch the address, and then it latches whatever garbage is now on the bus. You can see at the top is one of the bus lines, and you can see it's like mid-transition when that second spike happens, so it's latching garbage. And the way I fixed this was by simply putting a low-pass filter on this line to swallow the secondary, like, short glitched pulses. And that's, you know, if you remember the picture earlier of those PCBs, one of them had like a little chip dangling off the side, that's part of that. So, I mean, basically never ever and the clock. You should never process the clock signal in any way, because stuff like this will happen. This is actually a known issue, and in fact, when I've built that scrap CPU thing out of individual logic gates, this was like told to me like 10 times by different engineers. Do not do this. Do not process the clock in any way like that. Find some other solution with like negative triggered flip-flops or something like that. But all in all, this presents a little bit of a novel problem, right? Because I simulated this chip, I tested it in simulation, including the gate level simulation, which simulates like the individual logic gates, and it didn't show up. Like, this didn't show up in simulation, even though it could have, in iVerilog. So iVerilog is the default Verilog simulator that is used by the eFabless framework, and I decided to set up a simulation in Verilator on my own, and turns out it does simulate this glitch. So different simulators are giving me different outputs, and Verilator is supposed to be the imprecise one. So that's kind of weird. And the thing is, if it's like messing up simulating this issue of the clock edge, maybe it can mess up simulating other things in combinatorial logic. Who knows? Maybe there's some other edge cases that are being missed in simulation. And yeah, so yeah, I don't know what to say to this, because yes, this was a stupid issue, and really I should have listened to the advice that people gave me, which is I guess one possible takeaway from this. Because I remembered that advice when I was making this, was like, yeah, but I walked out doing scrap CPU, so I'm sure it's actually fine. It was not actually fine. I don't know what else to say. Maybe it's like a case of your final line of defense is your own intellect and experience, which, you know, in my case, I should have known better. Or maybe sometimes shit happens because of the simulator failures, which the simulations is supposed to be my safety net, protecting me from making stupid mistakes. So it didn't. I don't know. You choose one of these for yourself. The AS2652, I'm very happy to report, has 0 discovered bugs so far. The bugs.md file in its repository is still an empty file. And it can run at 54 megahertz. If you use the internal RAM, you can run it at 54 megahertz. You shouldn't, because it gets really hot. Like, I have to put like a little heat sink on the chip if I run it at that speed. And it earned a permanent spot on my breadboard. Whenever I need to like test something on my breadboard, like a little piece of peripheral, I use this CPU now instead of like an Arduino or something. And other people became interested in it. It was such a like novel thing to have like a whole walking 8-bit microcontroller on these open source processors that I drew some eyes to that project. Here's what it looks like, by the way. This is at the top right, you can see my little breakout board. This has my like little custom microcontroller on it, the AS2652, and here I am using it to like very crudely generate a black and white NTSC signal, because I'm trying to figure out some timing stuff in general. So, next tape out, although this one's gonna be short. Next tape out came with CI2406, which was a paid shuttle run. Some people approached me and were like, hey, we need your help integrating our ideas onto a chip. If you do this for us, you can do whatever you want with the remaining die area, and we'll send you some chips. So that was the deal. And this was on a different PDK. This was Sky 130 nanometers, which is a 1.8 volt core voltage but configurable I/O voltage process node. We taped out some retro stuff, a Z80, a 6502, an 1802. And an ADX305, just old 8-bit processors, because this was essentially like a preservation thing, is what the goal of this was. And I actually taped out scrap CPU, like the thing that I built out of discrete 7.4 series logic in like 2018. I was like, yeah, if I can make this into like a custom integrated circuit now. I know how to. And I was like, yeah, gonna do that. Gonna come full circle. And I also implemented a very long instruction word, explicitly parallel 32-bit CPU, which fetches and executes instructions not individually, but in packs of 3. And that was one of the most complicated things I've ever done. It takes up like a third of the die area. And unfortunately, while making scrap CPU on the 8X305, I reused my broken flash interface from QCPU that we've discussed. Because those chips were still at the fab when this was happening. I hadn't had them yet and hadn't discovered this problem yet, so I was like, yeah, I have this Verilog module that I can copy-paste. And that's, I guess, a lesson in its own. Sometimes it takes months between you fucking up and you finding out. And that's a problem because it means that you might make mistakes again. But here's what that looks like. This one's a lot less dense. Everything that's like a cyan color belongs to the VLIW CPU, just to give you a sense of scale. There's the main CPU of all the registers is the wide one. Below is the instruction cache, and at top are the free execution units that instructions get pipelined to. Very top right is scrap CPU, including memory. All 64 watts of memory that scrap CPU can address, and the CPU itself fit in that tiny little square. Whereas before it was this big set of boards that took up half my desk. So, well, I already know that the VLIW CPU has a broken iCache. It doesn't, like, if it takes a branch and the branch location is in the cache, it incorrectly fetches from cache. And this is an issue I discovered, actually, and there's some GPU issues as well. I discovered all of these issues, and I fixed them. eFabless sent the wrong git commit to the fab. They literally, what I assume happened is one of the employees literally forgot to git pull before pulling the layout and sending it to the fab. They were 3 commits behind in the repository. So it didn't get a bunch of my bug fixes. And some of the bug fixes I made were like top level timing issues. I did like some hold violations. I'm actually surprised it works. I got the chip, it works, except for the iCache issue. And they said, okay, we've seen we messed up. On the next shuttle in 3 months, we're just gonna fab it again for you. This time the proper commit, and then he went bankrupt. So we never those chips, like the fixed chips, actually got fabbed and got packaged. But eFabless went bankrupt before they could just ship them out. So the chips exist somewhere in the US. There's like a reel of chips with my fixed CPU on them, but I will never see them because the whole company, all of eFabless went to some liquidator that didn't give a shit about fulfilling the existing customer orders. It probably sold the chips off for scrap. Actually, it's probably been scrapped by now. So this brings me to my final lesson for today that I really want you to take with you. I really want you all to take with you. It is possible to commit no mistakes and still lose. And that's not a failure, that is just how life works. Which is also known as someone else fucked up, not me, it was that guy over there. It was not me. But yeah, what am I doing now? Messing with RTL, with RTL, HDLs, and digital-only stuff was fine for a while, but I've now set my eyes on the analog domain. I've made 2 custom standard cell libraries by now, which involves doing manual layout. So this down the bottom is a layout for the flip-flop that I created on GF180. And you have to do all of this by hand. You have to know what you're doing. And I also started messing with analog circuitry. And, well, with these new frontiers, I'm sure comes new mistakes. In fact, I already know of one. I taped out a test chip using my Sky 130 custom standard cell library, only to then find out later that there's like DRC errors in there. I'm not sure if that's going to break anything, but we're going to find out. It could actually just be completely fine. Here's what that looks like with analog. I mean, this is on GF180 again. I'm trying to build a circuit that generates the chroma component of a color NTSC signal, and that's what that looks like right now. This starts with a square wave and then outputs sine and cosine waves. And if I just duplicate this whole circuit and have a second one where the input square wave has a 90-degree phase offset, I get 4 sine waves, each with a 90-degree phase offset from one another, and you can choose to combine 2 of those waves and with an analog adder and some specific resistor values to generate any arbitrary phase offset that you want. So this is my first time learning about analog. It's confusing. It doesn't really compute in my head, but I'm doing it. Bonus tip. You actually get a bonus tip. I forgot about this. Documentation. Write documentation. For the love of God. I spend as much time writing documentations for my projects, as I do actually doing the projects. This is good not just for others who may want to use your chips, but also for yourself. Because when you have a project and you send it off to the fab and it takes 6 months or more to get back, you ain't gonna remember shit when that comes back. So you really need to write things down for yourself. You will need it. Just trust me, save my ass. I didn't even have to learn this lesson through any mistakes. It's just a lot of frustrated just days spent debugging just to figure out that I just rediscovered a quirk that I already knew that my project had, and I just didn't write it down. And also it really impresses people because you can just, if you have documentation of what you made, you can show it to people and they can look at it. Yeah, and this is what this looks like. So this is for the 8-bit microcontroller. There's some bus signaling documentation. And I also have this. I spend a lot of time on this. On the instruction set architecture documentation page, there's this table. You can hover over it and it gives you information on each opcode. And you can click on it and you can get to a description of the instruction, like a detailed description. And, well, that's it for the presentation. I'm definitely not done making mistakes. This is actually my second time doing this presentation, and it's gotten longer since last time. Let me put it that way. And I'm sure this will happen again in the future. V3 of this even longer. I could talk for hours about each one of the designs I've ever made, like the VLIW CPU, for instance. And maybe I will. Like, if you come up to me and talk to me, you can like hear some details that are not in the documentation. Currently, I'm working on more stuff, as I already said. My next tape out is already planned. I'm going to be taping out a bunch of replicas of retro ICs, like the C64 SID or the FIG2. Also making ICs to support homebrew developers. Because maybe I'll actually sell them. I'll make that a thing. Avalon Semiconductors is already the organization name that I publish all of my open source stuff under, so why not? And of course, yeah, Dad. I just put that there. There you go.
Woo! Woo. Oh.
Thank you. Clap, 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 clap.
I was the mouse for this other computer that I have, it decided to break today, and it sometimes double clicks. So I was using a keyboard to advance the presentation slides, and my arm hurts. I was holding that in such an awkward position. If anybody wants to ask something, here's the microphone, you can just come up here and you can take it.
Or alternatively, I'll bring it to you. Let's, this case, because of the group, raise your hand or basically go where Sky Dragon is. Just kind of stand in the middle of the air in this region here, and we'll start forming a line.
Okay. Oh, we have a line and everything. Wow.
I just had a soft crash. Awesome. I'm back. All right, Sky, you are definitely, well, the Sky Dragon, sorry, 2 skies in a row.
Hello. I was just wondering, you said you wrote that RISC-V CPU in 8 hours. What was the overall design of it? Was it a single cycle design, or did you do microprogrammed?
I do need a microphone back.
Oh.
Yeah, someone needs to.
Maybe do it at the stage. Maybe we walk up a little bit.
Oh yeah, maybe you should, if you just come up here.
Yeah, actually, that's a better. You're right.
Yeah. Okay. So it's really.
Don't forget to repeat the question, by the way, for the sake of the stream.
Yeah, you wanted to know the particular approach I took for designing in 8 hours a RISC-V core. Well, it's pretty much the dumbest way to do it. I just have a state machine where it just goes back and forth between memory access, execute, memory access, execute. Mm-hmm. With decode, it's sort of inline. It's the only thing that's optimized. But yeah, it doesn't do one instruction per clock. I didn't do anything complicated like that. It doesn't even have a cache, but it makes sense. It's supposed to be an embedded device, so that's suitable. Yeah. Okay, can you give this to the next person?
I can come up.
Thank you, Other Sky. All right. First off, thank you for the awesome presentation. It's awesome to see people like looking back at the past, all the hiccups that happened and stuff, and using that as a lesson for others. I think these are always the most memorable presentations in my opinion. And my question is, can you talk a little bit about like the process of simulating this stuff? Like what is actually going on under the hood of a hardware simulator that you're using? What's getting quote simulated?
Okay, so the question is about simulation and how that works. Well, I think the answer you're looking for is, well, there's two different types of simulation. There's RTL or gate level. Because, you know, when you're doing digital designs, you're programming that in a hardware description language, which is just the programming language that emits logic instead of bytecode. But, you know, because it's code, you can just run it like code. You can have an interpreter. And that's the easiest way to do a simulation. But there's also gate level where you take it. This depends on how exactly your flow works, how exactly you're generating the integrated circuit layouts. But most likely, when you take your RTL and you turn it into logic and you turn it into a chip, it's gonna one of the artifacts, one of the build artifacts you get is just a net list of logic cells, of logic gates, of just like there's this gate here and it connects there, and like its inputs connect there and there, and you can simulate that as well. Similar to the way like a logic simulator like Logism would. But for the most part, I'm not sure about the details of how the actual softwares work to do that simulation. What I have to do is specify test cases, and how that's done changes in the framework. CocoaTP is apparently the hot new thing in open source silicon, where it's just a Python program. You write a Python program that says like, okay, set this pin to high, this to low, wait a little bit, and then check the outputs, sort of how you would expect. It's like the reverse of programming in Arduino. And
Okay.
what I do is the framework that I use specifies test cases in Verilog. They function similarly, but I get a little bit more versatility when it comes to simulating specific pieces of hardware. Anyway, I hope that answered that.
Yeah, well, thank you. You can just come up here.
Hey, so first off, awesome presentation. I saw in one of your boards you used both a CPLD and the ASIC. Would you say that something like Tiny Tapeout would have any advantages for digital design over just using a CPLD and putting the Verilog on that?
Absolutely not. They're not born that badge. It had a $1 CPLD from AliExpress on it, and I can fit things onto that CPLD that I can't fit onto one tile on Tiny Tapeout, which costs I think like $150 entry price with PCB, and I don't think so. Tiny Tapeout is more interesting as a learning tool, as an academic tool, because it allows you to mess around and experiment around without having some kind of commercial goal. Or also analog, because CPLDs, FPGAs, that kind of stuff is digital, but you can lay out custom analog circuits on Tiny Tapeout, and I think that's a lot of stuff happening there. The most exciting things that I see happen in Tiny Tapeout are analog, in the analog domain. So,
Thank you.
Behind you.
Thank you for the presentation again. So you mentioned that you used a finite state machine for your CPU, but then one of your CPUs you had a lot of bugs because you're trying to optimize it. Would the finite state machine be kind of a bottleneck for that optimization? Would that not work well in that case?
Oh, hold on. Can you need your microphone back? Can you come a little closer? That. Thank you. I'm asking if the finite state machine is a bottleneck for optimization. I guess it's just if you're designing something simple like an 8-bit processor, it's fine to use an FSM. I don't know. I feel like if you do it right, you can still optimize it to a high degree. But I didn't do it right. Like that was beyond me at the time. And this is more of a failing of me misunderstanding how these things are correctly used, and then doing it wrong, rather than an inherent property of FSMs as being unoptimized or bad. Okay, I think that was the last one.
We have one more question from the Discord.
Okay.
All right. so I can.
Yeah.
So this question was actually asked at the very start of the lecture, so apologies if this is. How long does it take to do a tape out? Yeah, how much time does it take to do a tape out? That was the question verbatim.
Okay, give me that. Okay, so the timeline of a tape out changes where you tape out. For instance, a timeline that I remember barely with Skywater Foundries was that, or at eFabless, was that there would be a deadline to when you would have to give them your final layout. But, these shuttles would be regular, like one every 3 months, so you could kind of choose. And then you could work on your design for however long you wanted. It's really up to you, that part. The fab only really cares about you delivering the layout on time. And then, depending on what fab you choose, it takes a different amount of time to get fabbed. So this usually takes around like 4 or 5 months with Sky 130 or GF 180. And then the raw dies have to be packaged, which in this case means putting them into like a dip or QFN, like the physical like little package, plastic black package you put on your PCBs with soldering. And that can take another, I don't know, like a month or so. And then you get that shipped back. Unless, it's eFabless and there's like 6 months of delays repeatedly, and it takes like forever, and it's like worse than like modern video games. But but eventually you get your chips. But for the most part, you spend a lot of time just waiting around. I mean, I guess if you're rich, you can already start working on the next thing, but it costs a lot of money, so for me it was waiting. I need some water.
Yeah, talking for a while is thirsty work. Any other questions before we close the Q&A session? All right. You have any closing words, Tholin, before we close up the lecture?
I'm not sure. I really hope I really hope that people learn something from this. I'm not sure how many here in the audience do stuff with like RTLs and stuff. I know some of what I explained is not just applicable to integrated circuit designs, but also when you're doing stuff with FPGAs, for instance, or CPLDs or anything that's programmed like that. So I really hope that this has given people some stuff to think about, even in terms of software development. Some of this is good advice, especially the RTFM stuff. But yeah, I don't know. I don't really know. I mean, this was fun. So thank you all for listening. I have to thank everyone for like sticking through this.
Thank you for giving the talk.
I was nervous when I saw so many people, and I was like, okay, but it like I'm more surprised that I'm more surprised that everyone stayed. So.
Oh, that's actually pretty good.
Thank you for not telling. Thank you for not telling me that beforehand, because I would have been a nervous mess.
Oh no. All right. Well, thank you very much, Tholin, for their presentation on how not to do integrated circuits. It seemed like everybody really enjoyed it. Now, for the people who are on the stream who aren't really aware of what this is for DGen Tech. DGen Tech is a group on VR. We mainly meet on VRChat. We are a group of furries who are working professionals in the STEM field, STEM being science, technology, engineering, mathematics, and medical. And this is the capstone of our monthly lecture meetup, where we all meet up, we go talk to one another, and we have one member of the community be present on stage and talk about their specialization to the wider community. And then we have been more recently been uploading the lectures to YouTube, but we've been doing this for actually a few years now. So thank you very much for your interest and showing up and giving us your presence as well here in VR. We have over 30 people in this instance right now, and we have a community of, after the recent bot purge, we still have like over 350, I think, actual real members. So thank you everyone for taking part. This is the closure of our formal portion of the meetup. We're still going to be hanging out, so of course, just feel free to talk. K9 will be whenever they're ready for it, wherever K9 is. Whenever they're ready for it, we'll be doing our drunk movie night, which will be following this. All right, whenever they have that ready to do. So thank you, everyone.
And maybe one day I'll even make a presentation called "How to Make an Integrated Circuit," where I will show people how to actually create a project and submit to Tiny Tapeout. Yeah, that's what I'll know I've won. We'll see.
That's the paid version.
Paid lectures, so let's go. Write that down, write it down.
That's how it starts.
It is.
They're a subscription service. Let's go.
So
if you don't mind, I would If you don't mind, I would just
project, I guess.
open the portal like in around about 10 minutes.
I will say, Salix,
in about 10 minutes? Okay, sure. Yeah. Do you want to make that announcement?